Welcome to the deep dive. Today, our mission is getting into one of fusion's foundational concepts, something that's actually seeing a bit of a comeback, the Z-pinch plasma confinement system.
That's right. It's fundamental, but also, surprisingly elegant in a way. The Z pinch, or sometimes the Bennett pinch, it's where the plasma actually confines itself.
It confines itself. How does that work?
Well, you drive a really strong electric current through the plasma itself,
Uh-huh.
and that current, it generates its own magnetic field.
Okay.
And that magnetic field squeezes or, pinches the plasma inwards. The name Z pinch. It just comes from the current flowing along the Z-axis on a graph, basically.
Gotcha. Simple naming. And it started out aiming for fusion, but now we see it pop up elsewhere.
Oh, yeah. I mean, fusion was the original goal, definitely.
Yeah.
But nowadays, related devices are actually used as intense X-ray sources.
Mm.
And there are even concepts for space propulsion using the same physics.
Fascinating. So let's get into the physics a bit. You mentioned the current creates the field.
Exactly. Think about the Lorentz force. A good analogy is to imagine the plasma not as one thing, but as many, many parallel wires, all carrying current in the same direction.
Okay, like wires in a cable.
Sort of, yeah. And basic physics tells us parallel currents attract. So all those wires pull inwards on each other. The whole plasma column contracts.
And what stops it collapsing completely?
Well, as it compresses, the plasma's own gas pressure skyrockets, right? And eventually, that outward pressure perfectly balances the inward magnetic pinch. You get at equilibrium.
But you need a huge current for that, presumably? And plasma is very conductive, isn't it? Almost like copper.
Extremely conductive.
Yeah.
And that's the key challenge for powering these things. You can't really run them steady state easily.
So you have to pulse them.
Precisely. Z-pinch devices are inherently pulsed systems. They usually need enormous rapid energy sources. Think giant capacitor banks, maybe Marx generators, that can just dump colossal amounts of energy very, very quickly.
Because the plasma would otherwise just drain the power source too fast?
Exactly. The high conductivity means the energy gets dissipated rapidly if you tried to sustain it slowly.
Right, which takes us into the history.
Mm.
These ideas go way back post-World War II, right? Things like the perhapsatron in the U.S.
Yes, the 1950s saw a lot of activity.
Mm.
But they immediately hit a major snag, a big one.
The instabilities.
Especially the kink instability.
Right.
The nice straight plasma column just wouldn't stay straight. It would, kink, wiggle, buckle, and then slam right into the walls of the container.
Which obviously kills the confinement instantly.
Instantly. Game over for that pulse. So the first big fix came around, 1953, the stabilized pinch.
How did they stabilize it?
They figured they needed external magnetic fields, not just the one from the plasma current. The idea was to add coils around the chamber to create another field that would sort of twist the total magnetic field into a helix.
Like rifling in a gun barrel almost, to keep it straight.
That's a decent analogy, yeah.
Yeah.
It gives the plasma column some rigidity, guides particles back to the center if they start to stray.
And this led to that famous UK machine, Zeta.
Yes, Zeta, built in '54. Huge machine, huge excitement initially. It produced bursts of neutrons, which everyone thought meant fusion.
But it wasn't quite what it seemed. You said misleading results earlier.
Right. It turned out that neutrons weren't coming from thermal fusion, the hot, dense plasma core doing its thing.
So where were they coming from?
They were mainly from energetic ions within the plasma, getting accelerated by instabilities and crashing into the walls or residual gas. Not the sustained fusion they were hoping for. It was a pretty big disappointment.
But the underlying idea, the stabilized pinch, didn't just die out?
No, it actually morphed into something else. The core concept, using both the plasma's own field and external fields for stability, that heavily influenced the Soviet tokamak design.
Ah, okay. So Zeta's legacy is actually the tokamak, in a way.
In a very real way.
Yeah.
The tokamak basically took that stabilization idea but flipped the energy balance. It uses much stronger external magnetic fields for stability and a relatively weaker plasma current compared to the Z-pinch.
And that solved the major instability problems.
Largely, yes. It proved much more stable, and after about 1968, the tokamak became the dominant approach worldwide. The Z-pinch kind of faded into the background for a while.
Until now, perhaps. You mentioned a modern revival.
Exactly. There's this really exciting concept now called sheared-flow stabilized Z-pinch.
Sheared flow? What does that involve?
Instead of just static magnetic fields, use the plasma itself. You create high-speed flowing layers of plasma, typically in an annular shape, around the central pinching column.
So the outer layers are moving fast relative to the inner core.
Right. That difference in flow speed, the shear, provides a powerful stabilizing effect. It physically disrupts the formation of those kinks. It's really quite clever.
And this isn't just theory, is it? I read about ZAP Energy.
Correct. ZAP Energy, a spin-off company, has demonstrated this. They've achieved stability times something like 5,000 times longer than you'd get with a simple static Z-pinch.
Wow, 5,000 times. And they're getting fusion conditions.
They're getting significant results, reaching temperatures around 1 to 2 keV, which is, 12 to 24 million degrees Celsius. And crucially, they're generating reliable neutron emissions indicative of fusion reactions.
That's a serious comeback for the concept. And you mentioned propulsion, too.
Yes, there was work with NASA exploring Z-pinch for fusion-based propulsion. The idea is to use the intense energy pulse from the pinch to heat and accelerate a propellant, like lithium.
For faster space travel.
Potentially much faster. Some concepts suggested it could, theoretically, cut a one-way trip to Mars down to maybe 35 days or so. Still conceptual, but it shows the power density you might achieve.
Okay, so wrapping this up, the Z-pinch started strong, hit the instability wall, inspired the tokamak, and now it's re-emerging with this sheared-flow stabilization technique. Seems like it's back in the running.
It really does. It was sidelined for decades, but this new approach seems to overcome its main historical weakness.
So the final thought maybe is, should we be reconsidering its place in the fusion race?
I think that's the provocative question, yes. Given these stability gains, the potential for smaller, simpler reactors compared to, say, massive tokamaks, could the Z-pinch be the dark horse here? The one that might just surprise everyone? It definitely warrants keeping a very close eye on.
A dark horse indeed. Something for us all to think about. Thanks for walking us through that.
My pleasure. It's a fascinating story.